All right, so we are talking about topologies on a set. A topology is a description of what the open sets are in some kind of big space. And the standard example is like R, with the open sets being defined as in terms of epsilon neighborhoods. But there are other types of topologies that you can do. So I will refresh our memory about the definition of a topology is it's any way of choosing which are the open sets, and it has to satisfy the finite intersections property and the unions property. So I'm just going to refresh our memory, or I will write this definition again because this is super important. A topology on X, so X is the big space like R or something like that, is a collection of sets, which I will write with my fancy, that's a fancy looking T, a collection T of subsets, and the subsets are called open. So when I say open set in this class, I don't necessarily mean the thing about the epsilon neighborhoods. I just mean that I'm referring to certain sets as open in the context of a certain topological space. So a collection T of subsets, which are called open, such that, or satisfying, they have to satisfy these three rules. The first is that the empty set and X are open. The empty set and the whole space always must be called open, or else your definition will not lead to anything good. The second property is the, let me make sure I get them in the same order. I remember all the properties, but I usually write the finite intersections next. So it says if, well, let me just write in words. Any finite intersection of open sets is open. All right, and the last one, any union of open sets is open. If these three things are true, then you are talking about a topological space, and all of the ideas that we're going to discuss in this course will be appropriate in a topological space. Things like, if these are true, then you can talk about things like connected sets or compact sets or continuous functions. All of these things are concepts which only make sense in a topological space. And those three properties need to be true. All right, last time I encouraged you to think of these as kind of like the group axioms in group theory. They are the basic setting within which all of group theory takes place. If these three things are not true, you're not doing topology. You're doing something else maybe, or nothing else. All right. One thing that's a little frustrating about point set topology, I think, is that these rules seem to have nothing to do with anything, really. Unlike the rules for a group, I can say very clearly the associative property for a group is like the associative property for ordinary addition or whatever. These three rules, to me, they seem very abstract, and it doesn't really mean anything. I mean, there's very little intuition in these three properties. It took a very long time for people to settle on these three properties as the basis of all of topology. But we have, and this is what they are. All right. Some simple examples we talked about last time. So for any set, the classic example that you should have in your mind is the standard topology on R, in which X, the big set, is R, and the topology, the open sets, are the ones defined as open sets in terms of the epsilon neighborhoods. But there are other topological spaces, and the simple examples from last time are if T equals just empty set and X, that is to say, there are no open sets except for the empty set and X. That counts. That actually satisfies all three properties. This is called the trivial topology, and it's not interesting as a topological space, but often we will discuss it just because it's a simple example. Kind of like the number 0 is not really interesting by itself, but it's very important. Same goes for this. And then also so this one, the trivial topology, in which no set is open except for the ones that have to be open, the empty set and X. And then the other way around that you could make sort of a simple, stupid example is to make every set open. So if the topology is equal to the power set of X, that, remember, means all subsets. If you just say that every subset is open, then that is also kind of a stupid example, but it's called the discrete topology. All right. I want today to discuss a few other less stupid examples. Like those are examples that you don't have to work too hard to demonstrate that they are actual topologies. Does anybody have any questions before we get into some more specific examples? All right. We're really doing topology now. I can feel it.
Actually, I have one question.
Yes?
I forgot, what was X again?
X is the big set. So the idea is you start with some big set, which is kind of like a universe or the space as a whole, and then you say which of the subsets inside there are open. So in the standard setting, the big set is R, and the open sets are like open intervals or unions of open intervals. But it could be something else. X is the whole universe, so the big set. Okay, how about just simple abstract examples? Here's an example which has nothing to do with R or epsilons or anything like that. How about let's just imagine that X, the entire set, is just 3 things, A, B, and C. And my topology has to be telling you which sets are open. So what subsets of that are open sets? And I will tell you, just for the sake of making up an example, let's say my topology is this empty set, just A, and ABC. All right. So I'm imagining just an abstract set with 3 things in it, and I'm telling you the open sets here will be the empty set, because it has to be. Also, A by itself is an open set. And also, ABC, the whole thing, is an open set. That also, because it has to be. All right? So I could ask, is this a legitimate topology or not? You have to verify the 3 properties. So let's check it out. Is T a topology? If it is, then we can do topology with it, with that set. If not, then it's not. Is T a topology? You have to just think through the 3 properties, and in this case, it's not so hard. The first property, X and the empty set have to be in T. Is that true in this case? Yes, it is. You can see the empty set in the list there. So empty set is in T, and what about the whole set X? That's ABC, and that's here. So yes, ABC, the whole set X, is also an element of T. You can get a little confused with the element signs versus subsets. Should I be saying element here or subset? Actually, I should be saying element. T is a set of sets, so this X is one of the elements. It's right here, and the empty set is one of the elements. It's right here. All right. So actually, that's a little confusing sometimes. Anyway, what about the second one? Is about finite intersections. The idea is if I take any finite amount of sets, now there's only 3 sets total, so you could just imagine taking, say, any 2 of those sets. If you take the intersection, is it still one of those sets in the list? That's what I have to think about, is any intersection of sets in T also in T. So for example, I should be looking at something like empty set intersect A, right? Those are 2 things from T. When I take the intersection, is it also in T? And I suppose you could even write out all possible ones. There's the empty set intersect A, the empty set intersect ABC, and then there's A intersect ABC. And I think those are all the possible intersections that I can make. Or I could do the intersection of all three of them, right? But that would be it. So empty set intersect A intersect ABC. We have to just verify these answers. Are they still part of, or are they still sets which are in T? Well, let's just, this is not really tricky. What's the intersection? Empty set intersect A? What do you think? I want to know all the elements which are in the empty set and also in A. Yeah, that's the empty set. And empty set intersect with anything is always the empty set because there are no elements that are in the empty set. And so this is the empty set. And is that one of the things listed in T? Yes, it is. So this one is in T. I'll put a little check mark there. What's the next intersection? Empty set intersect. Again, empty set intersect anything is always empty set. So this is empty set again, which is in T. So that's good. And would you mind if I just jump to the last one? This is also the empty set because it involves the empty set being intersected with some other stuff. So this also is in T. The only somewhat interesting one is that fourth one there. A intersect A, B, C. What's the intersection of that?
A.
Yeah, just A. The set containing A, of course. And that is also in T. I can see it. It's in the list up here. All right. So this does satisfy property number 2. The finite intersections property is satisfied. So 2 holds. All right, and then we need to, for number 3, is the same but about unions. And it's not necessarily about finite unions, but infinite unions, but there's only 3 sets in here anyway, so the distinction is irrelevant in this example. You can't take infinitely many things and union together. Okay, so now I do unions, right? Same idea. We have to check all possible unions. In other examples, this would be a real pain, although in this example, it's easy enough. A union ABC, and then empty set union A union ABC. I don't know if you like this example. I don't know if you're worried deep down in your heart that the whole rest of the semester will be doing examples like this all the time. It will not be. This is kind of like defining a group operation using a giant multiplication table, and then you have to check by hand. Like sometimes you have to do that, but it's not typical. In this case, I told you what the topology is just by writing a list of all the open sets. That usually is not the way we're going to do things, but it is allowed. Okay, anyway, let's do the unions. What is empty set union A? Could we just like go across the room? Would you allow that? What do you think, Julia?
A.
Yes, the set containing A. All right, next, Alvin.
C.
I know all your names. Don't ask me the last names though, because I'm cheating with the Julias. Mike, right?
Yeah, ABC.
Yeah, this is ABC. Sorry, we're not going to get to everybody. And Julia?
A. B. Wait.
This is the union. That means you take all of these things together.
ABC.
Yeah, this is ABC. Yeah, great. Anyway, in all cases, these are all open sets, right? They're all in the list. And so, number 3 holds. Great. All right. And so, it is a topology. So, T is a topology. This is a set of 3 points in which I would say, according to this topology, one of the points is somehow special. Like A has a special role to play. A by itself is an open set, whereas B and C are not special in that same way. All right? T is a topology. So X with T, remember the terminology, we say X with T is a topological space. All right? I got some for you to try. I have 3 separate examples here. These are other ways that you could choose a topology on 3 points. How about your job is for each one, tell me which one is or is not a topology. So this one is similar to the one we just did, only it has kind of like two special points. Now, for the sake of doing this, technically you would have to write down all possible intersections and unions of all of these sets, which is kind of a lot. Let's just be slightly less formal about it, but you can at least think through in your head about all the possible intersections of these. Is it still going to be in the set, and also all the possible unions? All right, that's one example. I'll call this number one. Number two. I have three examples here. You tell me which one is a topology, which one is not. Sorry. I have a typo in that last one. I meant that. Maybe I'll give you a moment to think about it, and then we can talk about them. You should either say yes, it is a topology, or say it's not, and tell me which of the rules is violated about some intersection of something or other, or some union of something or other. All right, maybe we can talk about these, because I don't know if everybody's done yet, but as I was walking around, some people told me the first one is not a topology, and I agree. This one is not. Maybe I could ask the next Julia, did you have a counterexample for that one?
Yes, A union B.
Yes, if I do A union B, this is, of course, AB, but that is not in the topology that I listed. All right, so that means that this is not a topology because it violates the one about unions. All right, I believe the intersections rule actually is true for this one, but not the unions. Number two, what did you say? Anybody decide, is this a topology or not?
Yeah.
Kevin, yes, he said it is. Yeah, like I said, it would be a lot of details to actually try to write down every intersection and union of these sets. But just looking at it informally, I hope that you agree. If you take any intersection of ones with the others, it will not be it will be one of those things. Actually, one way to think about this topology, number 2, is this, apart from the whole set over here, this is all of every set which doesn't use B, right? And if you think of it that way, it's maybe a little easier. I hope you would agree. If I have 2 sets which don't use a B, and I take the intersection, that also is a set which doesn't use B. And similarly with the union, if I have 2 sets without a B, and I take the union, it still is without a B. And so this one is a topology. Is a topology. All right. And what about the last one? Did anybody have any feelings about the last one? Is or is not? Not? What? Can you give me an example which makes it not?
A union B.
Yeah, this one here. Yeah, A union B, again, is not in there. This would be A comma B, which is not in there. All right. This one also violates the intersection property. Did anybody notice that? If you did, does it violate the intersection property? Maybe not. Maybe it doesn't. I don't know. I thought when I was looking at it before, I thought it did, but now I can't see how. Maybe not. All right. Anyway, some things are topologies, some are not. This is kind of a cute, simple example. Most of the examples that we do are not going to be of this type, like I said. Usually we're going to be talking about sets which are more like R or Rn, and have interesting open sets defined. So let's talk one more example that I want to talk about is about a non-standard topology on R. All right. Everybody knows the standard topology on R, although the definition of the standard topology is pretty weird. It's a thing about epsilons, which if you've never seen that before, looks totally crazy on the surface. But here's one which is not standard. This is called the finite complement topology. And this is an example that's going to come up fairly often in the class as a non-standard topology that's still kind of interesting by itself. The examples we've had so far have been kind of made up and artificial, but this one is kind of interesting. So the definition of the topology is a set, let's call it U, a subset of R, is open in the finite complement topology when, this is what you would expect based on the name, R minus U, that is the complement of U, is finite. All right. So if the complement is finite, then we call it an open set. All right. I'm using the word open here, but another way to write this is you could just say T is defined to be the set of all U such that R minus U is finite. This is the definition of the finite complement topology. It is the set of all subsets U such that R minus U is finite. It is traditional, I'm not sure why, to use the capital letter U in topology to represent an open set. So I am often going to do that, and it's in the book. Unfortunately, depending on your handwriting, the capital letter U might look like a union sign, which is very confusing. So please put the little tail on the U, if you will. It makes it much easier to read because you are often going to be writing things like U1 intersect U2 or U1 union U2, which looks really confusing if you don't have a little tail on your U. All right, this is called the finite complement topology. And when I'm talking about R with the finite complement topology, I would usually write it like RFC. So if I just write R, then probably I'm talking about R with the usual topology. And if I'm, in general, in life in general, when I'm talking about R, I'm usually talking about R with the standard topology. But if I want to talk about R with some other topology, we write it differently. So RFC, it still means R. It's still like the real numbers, but it has a different topology to it. It's this topology about open set means that the complement is finite. All right. Oh, sorry. One technicality. The empty set does not have finite complement, so I have to say this: union empty set. That means the sets which are open have finite complements, or the empty set. The empty set always has to count as open in order for it to be a legal topology. So a set is open in the finite complement topology when R minus U is finite, I should say technically, or U is the empty set, right? The empty set must be included as an open set, or else nothing works in topology. Okay, anyway, let's, I would like to demonstrate this. So maybe I'll write this as a theorem. RFC is a topological space. We need to verify the three properties. So I'm going to verify 1, 2, and 3 for this topology. All right. And you're going to see some homework problems of this type where it says your job is, it says, let's imagine this or that definition for a topology. And your job is to either show that it is or show that it's not a topology. All right. Here, the proof is more interesting than that ABC example because we can actually say something rather than just checking a bunch of specific intersections and unions. All right. Anyway, we'll just go 1, 2, 3. 1 is basically always the easy one. Is it true that the empty set and all of R are open in the finite complement topology? Well, the empty set is open just sort of by declaration. I said specifically here that the empty set is part of the is an open set in this topology. So there's nothing to check about that. What about R though? R we didn't really discuss. R is open since, remember, open means the complement, that is R minus U, is finite. So if I want to show that R is open, I need to demonstrate this where in place of U, I'm using R. So since R, really I have to consider R minus R. What is R minus R? That would be the empty set. Yeah, the complement of the entire space is the empty set. And what I need to demonstrate is that the complement is finite. So the empty set, is the empty set finite? The answer is yes, even if it feels like maybe it's not. It is. Finite means it doesn't have infinitely many elements. And the empty set does not have, it has 0 elements, and 0 is a finite number. So yes, it is finite. So R is open since R minus R is the empty set, which is finite. All right. The empty set is finite. It really is. Okay, that's the end of number 1. Number 1 is always the easy one. Let's talk about number 2, which is about finite intersections. So for this one, I need to consider finitely many open sets. So when you are proving something is a topology, you always have the same basic structure. For the finite intersections property, I always begin by saying something like, let U1, U2, etc. to UN be open. Finitely many sets. That's why I only go up to UN. For the unions, you have to consider even perhaps infinitely many things. But for the intersections, you only need to consider finitely many things. So I let these be open. I want to say a bunch of stuff, eventually concluding with then U1 union blah 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 union UN is open. This is where I'm supposed to. Oops, sorry, off the bottom. This is where I want to end up, right? your argument has to start with a bunch of open sets and eventually conclude that the union of all of those things, intersections, sorry, I'm doing intersections now. The other one is unions. I meant intersection. Eventually concluding that the intersection of all of those things is open. And hopefully you can do that by, I don't know, some set theory arguments is what you have to do, all right? In this particular example, I'm talking about complements. So I can say, since, let's just take one of those U's, I'll call it UI. Since UI is open, we have here, this is also mostly boilerplate. Now you just sort of plug in what's the definition of open in whatever problem you're talking about. In this particular case, what does it mean that UI is open? Yeah?
R minus UI is finite.
Yeah, right. R minus UI is finite. Okay? All right, and what I want to show is the thing at the end. Maybe I'll say that at this point. I want to show that that thing is open. What is that thing? That would mean that R minus this intersection, right? U1 intersect UN. I want to show that that is finite, right? Because that's what it means for that thing to be open, is that the complement is finite. Can you do anything with this? Anybody know some kind of, is there something you can do with this? Just playing around with the set theory? Perhaps you remember a rule about the complement of an intersection. We actually talked about such a rule last time. Here's the point at which, at this point of the proof, you start looking back in your notes for, can I do something with that? I think one of the set theory things that one of my little set theory introduction things was this. This is x minus a intersect x minus b. This is a little different. It starts with unions, but the same is, or a similar fact is true of intersections. It's this. So these are facts about complements and related to intersections and unions. These are just true facts. These are really De Morgan's rules for set theory. But anyway, we can do that up here. So when I have R minus a finite intersection, I can rewrite this as R minus, well, I'll write it as is again. R minus U1 intersect, etc., UN. This is the same as R minus U1 union. The complement changes intersections to unions and unions to intersections. Burp, burp, burp. Union R minus UN. All right. And I'm trying to demonstrate that this over here is finite. Is that going to be finite? What this is a finite union. There's n different sets here. And I think we already said each of these things individually is finite, right? So this one is finite, the next one is finite. Each of these guys in the union are all finite. Sorry, I'm kind of running out of room here. I don't know if you left enough space. I can just do that. This is finite, right? We already said before that R minus UI is finite each time. So we said right here. And so what do you get when you take a bunch of finite sets? There's n different finite sets here, and you union them all up. The answer will still be finite, right? The finite union of finite sets will be finite. So R minus U1 intersect UN is finite. And therefore, that's the last thing that I need to write. That means that the intersection is open in the finite complement topology. All right. So fairly simple games to play with the set theory here. It does mean, unfortunately, perhaps, that you have to remember rules like this in order to do these kinds of problems. On our homework or something, I will expect you to look up those rules. On our tests, I won't expect you to remember really obscure things, although this, I would expect you to remember how to do this. All right. Any thoughts about that one? Let's try the unions. The unions hopefully will work the same way. And would it shock you to predict? We're going to use this rule for the step 2, the union property. In that one, I used the one about intersections, but the second one basically follows from the union property. All right. There's one weird bit of notation that we're going to have to use here. So this one is about unions. All right. The thing about unions is it's not necessarily finite unions. So when I begin this step, this is step 3. When I begin this part, remember for step 2 about finite intersections, I said let these be open sets where there's just finitely many. There's n here. When I'm talking about unions, actually, I'm not just going to write n of them because there might be infinitely many. And in fact, I'm not just going to write 1, 2, dot, dot, dot. Because there might actually be uncountably many. I don't want to write anything like a list of them because if I write them in a list, that assumes that they are countable rather than uncountable, and we are not allowed to assume that. So the way that this is done, this is a little weird. It takes a little bit of getting used to, I suppose, but I'm going to say it this way. Let U sub alpha be open for all alpha in some set A, where this set A can be any set at all. So this set A could be 1, 2, 3, 4, in which case the union I'm talking about is U1, U2, U3, U4. Or A could be all natural numbers, infinitely many, or even A could be some uncountable set like all real numbers or something like that. So this A here is referred to as the index set, because that's where this subscript is coming from. So you should think of this as something like 1, 2, 3, 4, 5 up to infinity, perhaps, but it might not go all the way up to infinity, or it might sort of go even further. It might be uncountable. So instead, we just say A, where A can be any set. This looks confusing. It almost never really matters in the proof. Luckily, we don't have to really worry about this a lot, but this is the way that you have to set the argument up. All right. And then what we want to show, well, could I just say, continuing like we said last time, so that means that R minus U alpha is finite for each alpha, right? And what do we want to show? We want to show that the union of all of those things is open. So I want to show the union, and the way I write that, rather than U1 union U2 union dot dot dot, because I don't want to write them out as if it was countable, this is the way we write the big union. So that is a big union, kind of like a big summation sign or something like that. And what this means is you take the union of all of those sets, where the alpha can be anything in my index set A. This is the big union. But you wrote the big union in discrete math class, right? I think so. There's also a big intersection. Okay, anyway, I want to show that this is open, i.e., what does that mean? That means R minus the big union, alpha in A, U alpha, is finite. That's what it would mean. That's what we have to show. All right. Once we've set this all up, though, it works out fine. So what this, I will say something like we have R minus big U, big union, I mean, A, alpha in A, U alpha. The notation here is a little heavy, but the argument is basically the same as in the first part. I'm going to take this complement of a union. It turns into a intersection of the complements. So this becomes big intersection of all the alphas of R minus U alpha. All right? And each of those are finite. All right? This is finite. And what I want to show is that this thing is finite. Well, is that finite? What I have is a whole bunch of finite sets, and I'm taking the intersection of all of them. The answer is yes, that is a finite set. Even if you only had two finite sets and take the intersection, it's finite, right? The intersection is automatically smaller than all of the individual sets that you're starting with. So even if this is an infinite intersection, uncountable, whatever, this is still going to be finite. So I will say any intersection of finite sets is finite. So intersection alpha in A, R minus U alpha is finite. And that's what we said we were going to show. So I will say shown. All right. You will have some practice on the homework doing similar things like this, but this is how to show something is a topology, something a little more interesting than those just random made-up examples. All right. Any thoughts about that? Any questions? Great. So we have 8 minutes remaining. I thought I'll just give you one little bit of terminology, which is not all that complicated, but I have to make a little admission. As a topologist, I always get confused with this terminology. I don't know if it's actually confusing or it's just like my own personal problem. But we have so far two different topologies that you could use with R. You could use the standard topology, or you could use this finite complement topology. So on R, we have sort of R, the standard, and then we also have R, the finite complement topology. Those are two different ways to discuss what it means for a set to be open. Or, actually, I should also say, we could also use the trivial or discrete topologies, right? Remember, the trivial topology is one in which nothing is open. The discrete topology is one in which everything is open. So you could also consider R with those ones. And I would like to point out, in this case, there is some sense in which, like, if it's open for one of these, then it's going to be open for one of the other ones. For example, if I look at an open set in RFC, the finite complement, looks like, if I were to draw a picture of an open set in the finite complement topology, that would be a set in R with finite complement. What that means is it has to include every real number except for finitely many ones which it doesn't include, right? The ones that it does not include is only finitely many. So an open set in RFC, if this is the entire real number line, looks something like it omits a few points. Maybe, you know, this one omits 4 points, but otherwise it includes everything. That's what an open set in the finite complement topology looks like. It includes everything in the real line except for a few individual points, all right? So an open set in RFC looks like that. What I want to point out, though, is that that set that I drew is also open in the standard topology, because this, you can write it as a union of open intervals. It's the interval from minus infinity up to this point, and then union with the interval in between these points. Those are open intervals together. So this set, this is also open in R, the standard topology. All right? So there's kind of a relationship between everything that's open in the finite complement is automatically open in the standard topology. But it's not true the other way around, because a standard open interval in R does not have a finite complement. If you just take an interval, the complement would be everything outside of the interval, which is not finite. That's infinite. So this, an open set in the finite complement topology, is also an open set in R. So in this case, we say, I would say something like, so this is also open in R. Sorry, I want to write down what I just said, but not all standard open intervals are open in the finite complement, right? If you take an ordinary open interval, just a single open interval, which is open in the standard topology, its complement is not finite, and so it's not also open in RFC. What I'm saying is kind of everything in this topology is automatically, if it's open in this topology, it's automatically open in this topology, but not the other way around. That means that this topology is kind of bigger than this one, because everything open in this one is also part of this one, but not the other way around. So we could say the standard topology is somehow bigger than RFC. All right. The standard topology on R has more things in it, right? There are more open sets in the standard topology than in the finite complement topology. So the terminology that we use for this, and this, for some reason, I've always found these words to be confusing, although, like I said, I don't know if that's just my problem or that they really are confusing. We say that the standard topology is finer than the finite complement topology, and the other way around, if you want to say it the other way around, the finite complement topology is coarser. Maybe I just don't like the word coarser. This is the terminology that is used than the standard. Finer versus coarser. The idea behind this is fine, sort of fine, looks like if I have a big set and I divide it into tons of itty bitty little bitties, right? That's finer. Whereas coarser is I divide it up but into like bigger bitties, not as fine. So this is coarser, all right? We say the standard topology is finer because it has more open sets in it, and those individual open sets can be kind of smaller than the open sets from the finite complement topology, all right? This is the, in our book you can see a nice, a very fancy version of this picture where they drew like a brick wall with big bricks here and a crazy stone wall with tiny little weird shaped blocks on that side. All right, finer and coarser. So the fancy way of saying this is if we have two topologies, you know, T1 and T2, and T1 is a subset of T2. That means everything that's open in T1 is also open in T2. Another way of saying that is T2 has more open sets than T1 does. Then we say T2 is finer than T1, and T1 is coarser than T2. All right? It's because T2, the bigger one, has more stuff in it, more itty bitties. And so T2 is called finer than T1. And conversely, T1 is coarser than T2. For topologies on the real number line, we have the finest of all, the one with, sorry, I'm gonna draw them left to right, coarsest to finest. The coarsest, the one with the least number would be the trivial. That is a subset of the finite complement topology, which is a subset of R, the standard topology, which is a subset of the discrete. The discrete topology is the one in which all sets are open, all right? And these ones, so these ones are finer, these ones are coarser. The finer ones have more open sets, the coarser ones have fewer open sets. All right, and I think that will do it for today.